So I was asked about continuity corrections when you use the normal distribution to approximate the binomial distribution. Now, in this question here, there is no way anyone would use the normal distribution to approximate the binomial distribution. But I'm using this one because there's smaller numbers to work with, and we can make a good argument about what we're doing with continuity corrections. So the first thing I want to do is actually expand out the binomial and find the answer to the question. Now, the question is that x is a continuous random variable that's distributed as a binomial. There's 4 Bernoulli trials that happen, and there's a 0.3 chance of success of each trial. So we can get, in this case, 5 options: no successes, or 1 success, 2 success, 3 success, or 4 successes. So there's 5 different options that can happen. So I can expand that out. And we're asked, what's the chance that our random variable ends up being bigger than or equal to 3? So the successes, there's 3 successes or 4 successes. Those are the 2 options, all right? So let's just expand it out, and then we'll have a look at what goes on there. So because, straight away, I've got the wrong coloured pen, because we've got a binomially distributed variable, we've got our success is 0.3, our failure must be 0.7 to be able to add up to 1, and we've got 4 trials happening. So in a way, that's the situation that we've been asked about. And we can expand that out. There should be 5 different terms in this expansion. The first one is 4C0 and 0.3 to the none and 0.7 to the 4. The next one is 4C1 and 0.3 to the 1 and 0.7 to the 3. The next one is 4C2 and 0.3 to the 2 and 0.7 to the 2. The next one's 4C3 and 0.3 to the 3 and 0.7 to the 1. And the last one's 4C4 and 0.3 to the 4 and 0.7 to the 0. Which nearly made it onto the screen. I'll just move that slightly along, slightly back, and you can see my expansion with all of those terms. So that, like I said, there's 5 terms: no success, 1 success, 2 success, 3 success, 4 success. That's what each of those items from the binomial expansion is meaning. Now, the actual question is saying, what's the probability that we have more than or equal to 3 successes? So we go up here where we can see 3 successes and 4 successes. Well, these are the 2 we want, so we're going to add those 2 together. So I'm going to get the calculator out and add those 2 together. So I've got 4C3 times 0.3 to the power of 3 times 0.7 to the power of 1, plus I've got 4C4, that's 1, and that's 1. So it's just plus 0.3 to the power of 4. And it's 0.0837. When I add these 2 together, I get my answer, and it's 0.0837. All right, or if you like, about 8.37%. That's the actual answer. There's no approximating there. We worked it out, and we can work out the probability of exactly 3 or less than 3 or bigger than 3 or bigger than or equal to 3 simply by taking each of those discrete probabilities and finding out the appropriate answer. Now, what if we were to do a graph of the probabilities against the random variable's possible values that it could take. So, for example, if I was to say the probabilities against the random variable having no successes, 1 success, 2 success, 3 success, or 4 successes. What if I was to do a graph of that? Well, I first want to know what each of those probabilities are. So I'll quickly work those out. So the probability for the first one here is simply 0.7 to the power of 4. The probability of no successes is 0.2401. 0.2401. All right, let's have a look at the probability of one success. It's 4 times 0.3 times 0.7 cubed. It is 0.4116. The probability of two successes is 6 times 0.3 squared times 0.7 squared, and that would be 0.2646. The probability of three successes is 4 times 0.3 cubed times 0.7, which is 0.0756. And the probability of four successes is just 0.3 to the power of 4, which is 0.0081. So if I was to graph those on my graph that I've written here, the highest I need to get up to is 0.4-ish. So to try and make it visible on that scale, we'll go 1, 2, 3, 4. We'll go 0.1, 0.2, 0.3, 0.4. And we'll pop in our graph. So 0.24 is roughly here. So 0.4166 is roughly here. 0.26 is slightly bigger than there, so there we go. 0.07 is there-ish. And 0.0081 is quite small there, a bit hard to see. Now we know that if the probability of success is 0.5, we have symmetry. So we still have, it's quite pixelated or jagged if we have a small number like 4, but the normal distribution might fit over it at least in a symmetrical way. But because our probability of success is a little bit smaller than 0.5, it's 0.3, then we're going to get some sort of positive skew, or they call it right skew, of our bell shape. It's not going to be a proper bell shape and symmetrical. Nevertheless, I'm going to go ahead and try and fit the bell curve to it, just to explain something about continuity corrections. So if I had a bit of a bell curve fitted to this, the bell curve might come up through here and back down through there, like something like that. Right? We've just got to accept this, because no one would try to do this for this small set of data with such a right skew situation due to the success being 0.3. But there we go. We have a kind of a bell curve fitted to there. Now, if I was going to use the bell curve for the normal distribution here that I've sat on top of it to approximate my situation where x is bigger than or equal to 3, what I'd be asking, this is the important thing to get out of this, what I'd be asking the normal curve to do for me would be to work out from 3 back this way if I just said, I want to know where it's bigger than or equal to 3, right? And it'll come back down in here like that area there. If I just found the z-score that was equivalent to x equals 3 in this, and found the area to the right of that, that would be one way to use the normal curve. But look at the situation. These columns with such a small number, these columns have significant width with respect to the whole situation, the whole graph. If there were 5,000, a width of 1 on a column is not significant, but because there's only 4, each width of 1 makes it quite a big significant difference. And especially when we're talking about the area. So when we look at this and it's, it might be going from there across to there, the actual question is saying success is bigger than or equal to 3. The actual question is wanting the area that I'm going to colour in red. It's wanting the 3 column and under that black and the 4 column. It's wanting the 3 column and the 4 column. And that's why we added this and this to get our answer at the beginning. Well, that's a lot bigger than just starting at the middle of the 3 column and heading out to the right. It's way too much bigger. So if you want me to include the value of 3 when I use the normal approximation for this binomial, I'm better off actually coming back to this beginning of the 3 column and including that. So I'll just colour in what I mean. I'm better off looking at how the normal curve from here right? How the normal curve from here is approximating the area of these 2 columns. That's a much better idea because it actually includes the column because it says it could be equal to 3, and you can see that that's looking much better. I know it's nowhere near it for this curve, but that's a much better approximation. In which case, I actually want to know where does the value 2.5 fit into the whole schema here. The z-score on, the standard normal distribution value, the z-score, that would be equivalent to a score of 2.5 in the situation that we've described. Now, we know we need a couple of things in order to work out a z-score. Because the z-score, sorry, just trying to get a pen that works. The z-score formula to standardise is where you take the actual score and you minus off the mean and you divide by the standard deviation. So we're going to need to figure out what is the mean of the normal distribution that we're fitting over the top of this binomial, and what is the standard deviation of that normal distribution as well. And then we can map it back to a standard normal distribution, and then we can use our knowledge of the area under a standard normal distribution to approximate the probability. So there's a few steps here, right? Now, fortunately, it's quite easy for a binomial to work out the mean or expected value, and it's quite easy to work out the standard deviation. So I'm going to do that now. The expected value for a binomial distribution is NP. So in this case, it's 4 times 0.3, it's 1.2. So instead of mu here, I'm going to put 1.2. Next thing I'm going to find is the variance of x. Now the variance for a binomial distribution is NPQ. So it's 4 times 0.3 times 0.7 NPQ, which is 4 times 0.3 times 0.7, which is 0.84. But that's the variance. So to find the standard deviation, I just do the square root of that. And I get 0.9165. All right? So I'm going to put 0.9165 underneath there. All right? So for the standard deviation, we find the square root of the variance. Now I'm mapping the normal distribution that I've fitted onto there back to the standard normal distribution to find the z-score. That 2.5 on this one would be equivalent to on the standard normal distribution. So I need to put 2.5 in as my score of concern there. So I go 2.5 minus 1.2 and I divide by 0.9165 and I get 1.4844. 1.4844, something like that. I'm not dealing with a lot of accuracy with this, so let's not get too picky there. My z-score of 1.4844 has what probability of being greater than it? Now, there's two ways I could work that out. I could go on my tables and see 1.4844, but that will give me the area up to that. So I'd need to subtract whatever I get away from 1. Or I could find the z-score for minus 1.4844, and that would directly give me the answer. So it depends on the table I'm given. So I'm going to assume that you've been given a table that only has positive values in it. In which case, you're going to have to go to 1.48, which is 0.93056. 0.93056 is saying the area up to there, or the probability of going up to there is 0.93056. But we wanted it to the right, so we have to do 1 minus this stuff in order to get what we want. So or I could just directly, if I had a table that would read negatives as well, I could have gone to negative 1.4844 or negative 1.48 and gone straight to the answer. If I go to negative 1.48, it's 0.06944. So I'm hoping that when I do that subtraction, I get the same thing, because I've just only looked at it on the table. So 1 minus 0.93056. And I get 0.06944. So that's the answer I get for this probability if I do it by putting the normal distribution on top of it. Now, it's not going to be a very accurate answer because there's still too much skew, because the number of trolls is too small, and also because we are a little bit off from the center in terms of our chance of success. But I was trying to more explain why and how you would use the continuity correction. If you were going to put a normal distribution on this, you wouldn't go and put a 3 into your z-score formula. You would put a 2.5 because it makes more sense to include that whole column. So you need to decide if you're using the column or not, and you're going to decide that by whether there's an equal sign or not. And you need to look at what's the most reasonable way of using that normal approximation. Now, just quickly, if you have one of these calculators, or something of the Casio 100s. I know that you can get away without using the table by going Shift 1, so you get those choices, and you want to choose the distribution, so you choose 5, and you get a bunch of possibilities there. The one that says P is giving the area from -infinity up to the z-score. The one that says Q is giving an area in between two different z-scores. And the one that says R, that's the one we're after today, the one that goes from the z-score up to infinity, like to the right of a particular one, which is what we're doing today. So I would press here 3, because that's my R, and then I would be able to put in the z-score to find the area. So the z-score that we're after is 1.4844. So I would be able to put that directly into the calculator to get the answer. Now you might look at that answer and go, that says 0.068852. 0.068852, that's different to what you got, right? 0.068852 is different. That's because there was no number in the table that was exactly equivalent to this value out here. The best I could do is get to 1.48, all right? So you can, guess in between two numbers where it might be if you want to get more exact, but you're kind of guessing. The calculator's being a bit more precise about what it's doing using the standard error function to calculate it. So these two are roughly the same. If you take it to 3 decimal places, 0.069, 0.069, they're still roughly the same.